let's go back to the example example 2, right, that we did for the 5 particles and everything. That we found that the net electric flux for this particular problem is just a summation of every single charge divided by the permittivity free space. And this is very easy to, from there, it's very easy to understand what the Gauss law is. All you have to do, you want to calculate electrical field for a given arrangement of charges or so on, is to create one imaginary surface that is called the Gaussian surface, and you have to calculate then the electrical flux for this particular surface that is caused by the charges that are enclosed inside the Gaussian surface. And that's actually very easy. Of course, not that easy, but sometimes it can be difficult, of course. But first of all, we have to calculate the flux. So the main trick, right? Since this is easy, right? You can choose where exactly, what kind of charges, where exactly you want to calculate the field. The main point here, guys, calculate the electrical field first. Of course, is choose which charges are you interested in finding the field, and then the next point here is how to calculate the flux that is caused actually by those, the flux caused by those charges, like crossing the Gaussian surface. To solve these, guys, easier, the simplest way of using calculating this, the flux, right? Let me put, is to use symmetries. You have to use symmetries so to make your life easier. So that's the best way of doing. And then, of course, let's look what we already know about symmetries. We have been solving some problems here, especially the previous 2 lectures, right? There are problems in static forces and electric field, and you use symmetries. We are going to do the same here to calculate the flux. We're going to use cylindrical symmetries, we are going to use plane symmetry, and we are going to use spherical symmetries to solve that. For problems that are more complicated than that, remember, you can always take like a very complicated geometry. You can divide this very complicated geometry in smaller parts that you can approximate some of those 3 geometries. You can approximate like these smaller geometries as cylindrical or planar or spherical symmetries, and then you can solve. Also, if it's too big, that's why you have then computational electromagnetism. So then you use a computer. But for problems that we are going to solve in the textbook, this is more than enough. It's too big, too complicated, just divide it. Yeah, that's a very good hint for life. If you have a problem that you think that is very hard to do, very complicated, almost impossible, just divide the problem in smaller manageable parts and take your time to solve. Good approach for life too. Okay, guys, since we don't have much time and I don't think I'm going to be able to solve all the today, I'm going to solve the first one. I'm going to apply Gauss law for this particular problem here. I'm considering infinitesimally long cylindrical plastic rod with a uniform charge density lambda. And I'm interested in finding one expression. Of course, you're always interested in finding one expression for the electrical field, right? Around a place located at a distance r from the central axis of the rod. Yeah, like exactly like is illustrated here in this figure or book. Again, we know Gauss law already. Know this, and we are going to apply Gauss law for this particular symmetry. Okay, what can you do here? Let's write here. We have three surfaces here, right, guys? We have this the top surface. The Gaussian surface is in orange here in this illustration, right? And this particular Gaussian surface it has three surfaces. We have this one that I'm just marking here, highlighting. This is a top surface. We have the bottom surface, and you have this lateral surface. This is the bottom, and you have this lateral surface, and this is the main point. You just separate. We are going to separate this integral here in three main parts. We're going to separate this. Mhm. We have this direction here, this direction, and this direction. Of course, the field for the lateral direction is radial, so it's going to be easy. Okay, but it doesn't matter. Let's just write here. We have then the first integral for the for the bottom surface is going to be the electrical field here, color product with that area right there, and this is top plus I'm going to call it going to be m integral. I'm going to divide in three parts. Bottom and I can write for the lateral and this is large enclosed there divided by this Gauss law. Guys, let's look here. First of all, this the electrical field, right? Let's make some considerations before we do anything. Let's just make some considerations, right? The the electrical field is radial for sure, since we have like a infinite rod. This direction here, if we consider the axis right like this, right? Clearly, this guy here is going to be completely radial. The electrical field is going to be in the radial direction, this direction, in cylindrical coordinates. The other guys here, they're going to be different direction, right? For example, if you analyze the top area, top, this the area there, the vector area there is going to be in the k direction, right? This one, the bottom is going to be sorry, it's going to be in the negative direction, right? And for the lateral one, this is going to be radial. well. If you calculate these scalar products here, this is going to be zero for sure. For the top surface, going to be zero. This is one way of analyzing this. The other way of analyzing this is actually, you can see that the normal vector is going to be perpendicular, right? If you consider, this is one way, right? Just analyzing this product between this, the scalar product between this, the electrical field and the elements of area, and you can see that this is going to be zero. The other way of seeing this without like too much calculations is realizing that actually we have like a normal vector here. Oh man, this is I'm calling this positive a hat, and then this side is negative a hat for the bottom surface. This is minus a hat, and then you clearly you can see that the angle of these vectors, you have k here and you have the er here, r hat, and then this is k hat, and this is 90 degrees, and of course this is going to be zero. You don't have to actually operate, right, the scalar product to realize that. Oh my god, we have time to what gives us only this integral here, right? And this integral here is easy to solve. Because then what you have here, this integral, since the field is constant, is going to be E times A, sorry, equals to charge divided by the, since we can write this one function of the line charge density, and write this or in this case here size, and we know that this area here, the area of a cylinder, lateral area, this is going to be 2 pi, the radius by 8, and if you do everything else, substitute here, you can find that actually the electrical field can be reached 1 over pi 0 and this is way easier solved than the way actually is classically solved. As you can see, in 3 lines I could solve this very easy, solve using Gauss law. Okay, so this is a solution using Gauss law. If you try to use, look guys, I'm going to show you the classic solution if you guys want to try. Where is that? Classic, look, the classical solution here is extremely long, and once you find the expression for the electrical field, you have a very difficult integral solve. Not quite difficult integral, but kind of complicated. It's going to take some time to solve if you try to solve using the electrical field method. So this is going to take a long time, look, to find the same expression. See, This is the final expression, but it takes a lot of work. And this is the biggest, I think, advantage of using Gauss law. Gauss law makes everything really, really simpler, as long as you choose proper symmetry and you choose like a proper Gaussian surface to solve your problem. And with this, I would like to end my today's class. I know this is kind of complicated, and we still have next class. I'm going to go through the Gauss law for planar symmetry, Gauss law for spherical symmetry. Okay, we're going to finish here because we don't have more time. This is a little bit longer than I expected. Any questions, guys? Questions?